Hello everyone, welcome to AITech or Tech Talk. My name is Kesar Chandra, roll number 584. Today's topic is discovering documentation for Java Container Class. So let us discuss more about this topic. The abstract of this topic is modern programs make extensive use of reusable software libraries. For example, we found that 70 to 30% of the classes in the number of large Java applications use the container classes from java.util.package. Given this extensive code reuse in Java programs, it is important for the reusable interfaces to have clear and unambiguous documentation. Unfortunately, most documentation is expressed in English and therefore does not always satisfy these requirements. Worse yet, there is no way of checking that the documentation is consistent with the associated code. Formal specifications present an alternative that does not suffer from these problems. However, formal specifications are notoriously hard to write. So this is the abstract. To alleviate this difficulty, we have implemented a tool that automatically derives the documentation in the form of formal specifications. Other tool props Java classes by invoking them on dynamically generated tests and captures the information observed during the execution as algebraic axioms. Although the tool is not complete or correct from a formal perspective, we demonstrate that it discovers many useful axioms when applied to the container classes. These axioms then form an initial formal documentation of the class they describe. So this is the abstract of this topic. So next slide is the introduction of the topic. One of the hallmarks of the modern programming languages is the support for reusable code. This support comes from both in the form of the language features such as inheritance and through extensive libraries for commonly used functionality and data structures such as hash tables. Language support allows users of the languages to create their own reusable libraries to distribute these widely, which shows in the figure 1, gives the number of the users or several number of the classes in several Java applications that use the reusable container classes from the java.util.package. So we see that the significant fraction, uh, sorry, we use the significant fraction of a class in Java application takes advantage of these reusable containers. Since the Java applications rely on so heavy on libraries, it is crucial for the libraries to be documented in a clear and unambiguous fashion. Moreover, we would like the documentation to be at least somewhat machine checkable so that library writes and user can automatically detect the documentation and code start to diverge. Today, most documentation for reusable code is written in a natural language. Example English for the documentation of the Java standard libraries, which is not mission checkable. Moreover, natural language sometimes unclear, ambiguous, or incomplete. To derive an algebraic specification from a Java class with a statistical analysis, we would need to model the full language semantics that uh, then abstract statistically from complex uh, heap-centric manipulations of implementation data structures into a concise, expressive algebraic specifications of the externally visible behavior. More precisely, so for Java and similar languages such an analysis is hard, since the language semantics are complex and only informally specified. Native calls, reflections, and dynamic classes loading can further complicate analysis. In contrast, A dynamic analysis can attack the problem of finding specifications from the opposite direction. Instead of trying to abstract the implementation details to intended high-level behavior, a dynamical analysis can probe the classes for the from the outside by observing how uh, concrete instances behave in practice. Based on the results of the probing, the analysis can formulate hypotheses on the behavior of the given classes and attempt to refute those. The next thing is the background. Background of this topic is our system discusses the documentation of the Java classes using the notations described in our prior work. This notation is designed to be close to the Java programming language to make it easier for Java programmers to understand the discovered documentation. To illustrate the documentation language, figure 2 gives the full documentation of one of them for an object stack class in our language. Our our document notation is based on the algebraic specifications and thus has two parts: algebraic signature and set of axioms. The algebraic signature itself has two parts. The the algebraic signature has divided into two types, and this it contains one of these sorts, and next one is the operation together with their signatures. Intuitively, sorts give the types of interest to the underlying term algebra, whereas operations are the concrete entities for from which terms in this algebra are built. Sorts fall into two categories: sorts which are used by the specifications and sorts which are defined by the specifications. So you can see in this there are two types: the sorts which are used by the specifications and which are defined by the specifications. The latter must be listed explicitly. So the figure you can see here is the figure 2 example specifications for an object class stack class. So you can see here the specs dot name, and here is the code for the sorts which is discussed in the previous slide. You can see it here. Class object stack is edu.colorando.cs that simple lead ts object stack. So this is the sorts and operations which are done in this program. So there you can see here axiom 1 is a for all s object stack for all o object. These are the functions you can see: pop and pop so, gto and gts. So these are the three axioms. These are the it's written in this program. So by importing this using this java util dot no such element exception. So these are the algebraic axioms. The axioms equate terms in this algebra. They are in the equality operator. So equal to gt specifies that the two operands are observationally equivalent. Equivalent in terms, general term equivalence as defined in the terms rights, while the exception operator throws specifies that the left-hand side, when is executed, throws the exception given as the right-hand side. More precisely, given in a Java method named m defined in a class represented by a sort CLS within the n arguments, argument 1 to so on up to argument n of the sorts. So sorts also it is given as sorts of argument 1 to so on up to sorts of argument n with a return type represented by a sort return. We constructed with the signature of an algebraic operation M with an algebra CLS as follows. M CLS sort argument 1 to so on up to a sort of all arguments n and tends to CLS X return. So here RET is used keyword used for the return purpose. The receiver argument of the sorts CLS or to the left arrow characterizes the original state or passed into M. The return type to the right of the arrow represents the state of the receiver after executing the M. So the right hand side part is the arrow included the return value of the sort rate and which can be of sort void. If the operation corresponded to Java constructor, the receiver argument to the left of the arrow is of sorted void. Note that our full specification language can capture side effects of the argument, side effects to arguments. This presentation of this paper assumes that invoking a method may be only can modify the observable state of the receiver and return a result. We have not found these limitations to be a problem for axiomations of the container class. So this is a discussion about the figure 2, which says about the axioms and the sorts, which is classified into two types. And next slide, consider the first two axioms in this line. And in these lines, in figure 2, the dot retrieval and the dot state qualifications select elements from the result tuple. Dot state retrieves the first element, which is the possibly modified receiver object is, and dot retrieval retrieves the second element, which is the method's return value. Both the axioms are universally quantified all over the overall object stacks and all objects. In our language, universal qualification over type excludes the special object now. So it is a this is important to ensure the receiver or no, non-trivial axioms which use as a null parameters are therefore specified separately. So which is shown in the figure 2, that is the axiom 1. You can see this in the previous slide. One sec. So here is the axiom 1. So in this you can see that for all as object stack for all O object here to perform two operations like pop, push and S and O. Here S denotes the object stack and O denotes the object. Dot state dot retrieval equals to T. So here you can see that uh, the states that invoking pop and push returns the object that was last pushed. Axiom 2 states that the invoking pop on an object stack right after invoking push reverts the stack back into its pre-push state. These axioms concisely and clearly documented the interface of the object stack except for the error conditions, which express the error conditions by relating terms to the exceptions with the binary relations throws in an axiom 3. This axiom specifies that any attempt to pop an object of an empty stack will raise a java.util. No such element exception. Discovering algebraic specifications from a Java class. We discover algebraic specifications automatically from the Java classes. The discovered specifications use the notion illustrated in the background part. In some cases, this means that the axioms must be duplicated if a class behaves identically for null and non-null parameters. This is minor inconvenience that does not arise very frequently and could be addressed with a slight extension to the type system. So you can see the flowchart pic in this architecture overview of our tool for discovering algebraic specifications. And here you can see the first term is a term generator and which converts it to terms, and the next is a equation generator which sends to the users, and the general term equivalence which are all connected to this axiom generator. The sound statistic analysis of discovering algebraic specifications from the implementation is impractical. For illusion, for illustration, consider the axiom for all a foo a dot state bar a dot state. To discover this axiom, a statistic analysis must be at least to prove that given an instance of a foo and bar will generate the states that are equivalent. This subproblem is undecidable, and to our knowledge, no conservative solution exists that generates useful results for real-world programs. Note that foo and bar may arbitrary methods use Java reflection, etc. Our dynamic program analysis approximates a solution for the equivalence problem by recording the observable behavior at runtime and validating its observations with tests. Continuing with the above example, instead of the proving the our dynamic program analysis approximates a solution for the given equivalence program by recording the observable behavior at runtime and validating its observations with the test. Continuing the above example, instead of proving generate an equivalent state, we observe the equivalent state for a number of examples of A. Unless we find the evidence to the contrary, we optimize assume that the equivalence holds. Therefore, by missing a counter example, we may report in an incorrect axiom. While it is unfortunate that we can only guarantee soundness for behavior that is covered by the test, we run prototype systems performed well with all real container classes that we tried. So this is a flowchart which shows the all the object stack examples and the flowchart. This is the object we have created in a previous program, that new object stack. This is the dot state classification. So from that it goes to pop. Mm, we then generalize the relation into axioms by replacing subterms with universally quantified typed variables to determine with some probability whether these axioms hold. We check them by generating test cases. Finally, we rewrite our axioms to eliminate these redund, reductants. So, so this is automatically mapping Java class to algebras. Due to the design of our specification languages, Section 2 mapping from the Java classes to algebraic signature is trivial. Each Java type is a sort in the algebra, and each Java method is an operation on the appropriate sorts. For example, our systems determines sorts and other operations declared in lines 2 and 7 of the figure 2. Automatically from the object stack class, the system queries the Java reflection API at runtime to find the methods that belongs to the input class and the argument and return types of the methods. Generating terms, the term generator, often abbreviated as a generator in this section, emits endless stream of terms. Each term models is a particular object state. For example, the following two terms model both model the same of state of an empty object stack. New object stack dot state, pop push new object stack dot state, object at the rate 7 dot state. Here, object at the rate 7 refers to the particular instance of the object class. Terms serve the role of test cases in our discovery tool. Therefore, the term generator goal is to produce the terms truly explore the state space of the input class. Thus, the generator produces terms that end with a dot state and not with a dot retrieval. We generate terms ending in dot retrieval in in a state in a separate space. Growing terms to generate a term for a particular algebra, the term generator first constructs an operation application corresponding to a Java constructor invocation. For example, to generate a term for the object stack algebra, the term generator starts with a new object stack as shown in figure 4a. The term generator then grows with the term incrementally by adding one operation application to the one Java method invocation at the time. Whenever the addition of an operation application causes the terms to generate an exception when executed, the term generator backtracks because growing an exception terms further does not normally retrieval instructing behavior. And this is the testing process of the Java container class. Woodward describes the methodology for mutation testing algebraic specifications. Mutation testing introduced one change to a specifications to check the coverage of a test set. Woodward system include a simple test and generation method that uses the signatures of specifications. Algebraic specifications have been used successfully to test implementations of abstract data types. One of the more recent systems is allows the users for test algebraic testing of OO programs in the presence of side effects. Quadrat is the automated testing for Java programs. Quadrat translates given method preconditions and post conditions into Java predicates and generates an exhaustive set of test cases within a fi- finite domain using precondition and predicate and checks the correctness of the method by applying post condition predicate. Our approach for generating term borrows ideas from Quora. Conclusion. Java applications rely heavily on reusable container classes. In our study, a number of large Java applications, we found up to the 30% of the classes in our applications used one or more containers in the Java.util package. Thus, it is important for container classes to be documented. To assist in this task, we described a documentation discovery tool that automatically describes algebraic specifications of a Java class, and since algebraic specifications provide clear and concise and unambiguous description of the interface of container classes, they are ideal for documenting these classes. Finally, we show that our benchmarks that tools produces may useful axioms and find that axioms are usually correct. And thank you.